start recording and then start sharing again. There we go. Okay, I am screen sharing and this meeting is being recorded, hopefully. Let's see, Zoom. What is going on? Okay, yeah, I can see this. It's getting recorded. All right, cool. So problem 11A var 3. There we go. Did I do this correct? Yeah. All right, cool. So you want to place a mailbox. I have two solutions. One is the brute force one, where I basically like place it. By the way, I assume that all the buildings are just like right next to each other. So the brute force algorithm has the minimum cost. So I basically name it cost. So you can define as cost by the number of each number of people in each building multiplied by the absolute value of the difference of the position of the building and the position of the mailbox.
Yeah.
So the way I do it is I is the proposed position of the mailbox and I have a cost. So I basically go through all the buildings and I calculate the cost. And if this is the minimum cost, then I will basically, and note that we can have multiple minimum places, by the way. Like just keep a minimum places and then I will append to it. And then if cost is less than that, I will just like add it, blah, blah, blah. And then I will return the first item in the minimum places, right? This is the brute force algorithm and it worked and passed all the tests. So I had something to work off of.
So you just try all of them,
sorry?
right? So you just try all the places?
Yeah, I just tried all the places. And the complexity of this is pretty much, if we have M buildings, I'm going through all of them. Like I'm going through all the positions and then every single time I'm looking through all the buildings.
Yep, and then every time you calculate.
So yeah, if we have N buildings and M people in them, this is all of, sorry. Oh no, it looks like it's recording. Okay, cool. Oh wait, sorry. So continuing on what I was saying, sorry, it started playing the last recording. Okay, so let's go back here. Okay, what we have here is, sorry, yeah, I was gonna write down the complexity of this. If we have N buildings and then M people in them, it will be O of N squared times M, right? And then, so now we have the better solution. And this is where I try to kind of like come up with a, think about it. So this really gave me kind of like center of mass calculation vibes where I just, it kind of was like, like a problem where you have to calculate the center of mass of something. So I basically just like wrote it down on the paper and I basically had to find the cost function and how it changes with as you like move around. So over here, if I had a pen and paper, I would be able to explain it better. But as you were explaining your solution, I think I came up with a slightly better solution. So let's say we have a cost at position I, right? And then we move to the right, right? So we just want to examine how the cost function changes.
Yeah.
Right? So for all the buildings to the right side of I, the cost function will reduce by how much? It will be exactly by the number of residents to the right side, right? Because for each resident will have one less step to take.
Yeah.
Right? So irrespective of their distance, so it doesn't really have to say about like how far they are.
Yeah.
As long as we move right, like we position the kind of postal place like 1 meter to the right, everyone on the right will have to walk 1 meter less.
Yeah.
And then long as we move to the left by 1 meter, everyone to the left will have to walk 1 meter less, right? So the optimal point is the point where we have the same number of people on the left as the same number of people on the right, right?
Because not the same number of people, the same same total distance they need to walk.
No, it doesn't have to do with the same total distance.
Because you have to do the initial calculation, like the total number of the total distance the left has to walk and the total distance the right has to walk.
No, it doesn't really have to do with the total distance that they have to walk. That's the thing. So if you have, for example, like only 2 buildings at like 2 like far positions, anywhere between those buildings is an optimal solution. Because as you walk towards right, let's say you have 2 buildings and then they have the same amount of people, right?
Yes.
The optimal place is not in the middle. The optimal place is anywhere in here. Because as you start moving right, everyone here has to walk 1 meter less, but everyone here has to walk 1 meter more. My background is not really helping with this. Let me actually remove my Zoom background. Wait, no. Okay. Virtual background, none. Okay, there we go. So if you have like two buildings with the same amount of people,
I see exactly what you're saying.
every single point in the middle will be an optimal solution.
Yes.
And if you
Yes.
have two buildings and one of them has more people than the other one,
Yeah.
then you definitely have to put the postal code right on this building. Because at every single point in the middle, if you move towards the right, you are moving towards the optimal solution because all the people here have to walk less, all the
Yeah.
people here have to walk more. But the difference of them will reduce the cost function, which is like if you have the cost function here, the
Yeah.
gradient is in this direction, right?
So you just keep walking until you have the left and right number of people equal.
Exactly. So that's just the problem. That's just the solution.
I think that's true, but it's not the same for center of mass because center of mass is
Not no.
multiplicative.
Yeah, yeah. No,
That's why.
center of mass is different. Center
Because
of
I was
mass,
like, wait, if you have like two like weights here, and then you put the like if you put the point of rotation or like the like some if you try to find the center of balance here,
yeah,
like if you move here, the shit's definitely falling over. But that's because it's a function of the like multiplication of the distance from the point. But here it's a subtraction
it
or
is
an
subtraction.
addition
Yeah.
or whatever.
So there's basically like a negative sign here that kind of makes it different than a center of mass calculation problem. But that's where I got the idea from. So it
Yeah.
didn't end up being exactly like that, which was very counterintuitive because if I had two buildings, I was constantly, I couldn't keep my mind off of thinking
That is
middle
amazing.
is the optimal solution, but it's not.
That is so true. Yeah, I
Or
think.
if you have like a big building here and a small building here,
Yeah.
I would think that, like, for example, the optimal solution would be somewhere in the middle, but closer to the
Yes.
bigger building. But it's not. It's exactly at the biggest building.
Yeah. You can
So
put it
that,
at the biggest building or at the smallest building, right?
well, if you put it at the smallest building, that's like the worst of the two.
Oh yes, yes. Sorry, sorry. Yeah, yeah,
Yeah, because all the people in
yeah,
the
yeah,
big building have to walk towards it.
yeah,
So
yeah,
what I
yeah.
do is that I calculate the total residence. So this is linear time, and then I just do a one pass, and then I basically keep a count of like where I'm adding on top of like all the residents that are to the left of this building. So
Yeah.
this basically gets solved in linear time.
Brother, this is an absolute gorgeous solution.
And then it's also like constant space because I am only keeping
Yeah, yeah.
residents to the left.
Why is this so beautiful? This is actually fantastic.
It was
Wow.
interesting. It was really interesting. But I was a little bit skeptical. I thought I understood the problem wrong because didn't really have to do anything with the original problem where you had to have a pivot and like look to the left of the pivot and right of the pivot and all that kinds of stuff.
I think Vlad
Yeah,
just
I just went straight for the pivot.
Yeah. Yeah. No, for me, it was kind of like I thought that I maybe understood the problem wrong or maybe like
Yeah.
my solution had a problem or something. But yeah, like, I'm glad this happened. But yeah, it's kind of like I don't really see the relationship between this problem and the pivot problem, or like the 11.8.
Even after I explained it and like showed my thing.
Well, yeah, like with your solution, I can see the link between your solution and the
Yeah.
original problem.
Yeah, it was so hard to find something logical to link it to that. Because I was like, what
Yeah.
the fuck? Like, what are they, like, where do I put this pivot? But
But
it does,
your solution, you are moving right and left. And the only part that is similar to the original problem is how you traverse through this list.
yes, it's
So you don't
only,
really like radix sort or like, reorder elements or anything.
no, you're just, yeah, it's just how you're doing a pivot and then hopping from left and right.
Yeah, so it's your
Yeah.
randomized pivot
Yeah.
choosing in the beginning that is similar to the original question. So I don't even think your solution is that similar to that.
Yeah. Wait, so I'm just thinking mine is like very similar to yours, except I keep so like, yeah, you do the calculation once and then you can just keep updating, but could I have done that too?
I mean, for me, I already knew that like you should just move towards where you have an equal number of people to your left and right.
But what if you did your exact solution but kept breaking it up into sub-problems? Like what if you guessed in the middle and then moved it to some other, but then you'd have to calculate.
I would have to still calculate the number of people to my left. And that's a problem. I would have to recalculate it every single time. Whereas here, I just go from left to right and keep counting and adding to that kind of value that I have.
Yeah, wait, because if you did it in halfway, you could have like count of left and right, and
Mm-hmm.
say like moving left is better. So you go halfway, but then you keep this count, so you know the total distance here.
Mm-hmm.
But and then you know this distance, right? Because you know the distance here, so you can increment all these people like in linear time, not in linear, like constant time, because you just multiply by this
No, it
distance.
would be linear because it's like half the buildings.
No,
You
I'm
would have
saying
to
like
literally.
this half, you know the number of people, and you know the new distance difference from the previous pivot and this one. So this whole like right chunk, you can instantly know. But then
Yeah, you can
these
add
new
it.
chunks, you'd have to recalculate,
Mm-hmm.
and then you'd have to do that again for another half problem, and that's assuming you get a half. So yeah, there's but the calculation would only be twice the length of the thing in on average, like twice the length of number of buildings instead of every single time.
But the problem is you need to know whether the number of buildings to your left are bigger than your right or smaller to know where to go next.
Yeah, but that's really easy because you have that as soon as you did the calculation for the total. Like if you calculate the
Oh
total,
yeah, if you calculate from the total, you just like take the number of buildings to the right,
yes,
which is like minus
yes,
to the left.
which is exactly what I
So
do.
you pick some random position and then you calculate all the ones to the left, and then you know all the ones to the left, and then you know
Yeah,
all the ones to the right,
yeah,
right? So for that, you're paying like linear,
yeah,
or like at least the first time you're paying
yes,
like n/2.
yeah,
And then you will know which direction to move in, and then you
yep,
will pick another random position.
yes. Within that one of those halves,
Yeah,
one of those
within one
left,
of the halves. Yeah,
and the other half,
and
you instantly know the number of people, and you know the new
and then you will
distance.
also know again because you have like a smaller subset, and
Yeah,
then you will also know the total of it. Yeah, it's basically the same complexity in terms of complexity
I
as
think
this
so too.
because it's n/2 plus n/4 plus n/8. I mean, like on an average case,
Hmm.
assuming that you pick in the middle every single time. Um,
But this one is just so logical to understand. It's
but
so beautiful.
yeah, it's like in terms of complexity, I don't think it would be any worse than this. I think they will be
Yeah,
this,
yeah, yeah. I think so too.
but I think this is easier to understand. But
Hmm.
that is a different like I could definitely see that being useful. Like I mean, that's how you do like what's it called? Binary search,
Yes.
right? That's basically binary search, except you're picking random at like picking
Yeah.
that instead of picking middle.
Yeah.
Cool.
All
Yeah.
right. I think we're done here, but this I'm still amazed. Like just that logic of the center of mass thing, and then the diff. Oh,
Yeah, it's interesting. Sometimes I just like bring the physics into the coding. And it works out.
Nice.
Yeah. All right, cool. Who's
All right,
taking 12P2?
Zia, take away 12P2.
All right. I forgot what that problem was about. Can we go to the problem?
Yeah, let's go. I'm gonna show it real quick. 12.2. Write a program which takes text for an anonymous letter and then a text for a magazine and determines if it is possible to write the anonymous letter using the magazine. The
Okay.
anonymous letter can be written using the magazine if for each character in the anonymous letter, the number of times that it appears in the anonymous letter is no more than the number of times that it appears in the magazine. So you basically have two strings. You want to see if you can write one string with the other one, and you can't reuse characters. That's basically what it is.
Here. Okay. I just switched to my solution.
All right. Oh yeah. Okay. You don't want to screen share?
Uh,
Ziad.
it's a pretty simple problem. So.
Okay. 12P2 Ziad. There we go.
All right. So for here, I have three solutions. Two of them are pretty close to the book. I still thought it was a good idea to include in there because they're pretty cool. One of them is something that I just did myself. You'll see some like red underlines here. That's again because I wasn't using this. It was just like kind of doing it on a separate ID and just like going from there. All right, but the logic is pretty straightforward. So we've got two strings and making this as quick as possible because we're going like way over in terms of time. So the idea is that by using a hash table, you kind of like just going over my own solution, method one. in here, what I do is I create two different hash tables. One of them that keeps track of all the characters in the letter text, and another one that's exactly the same that builds a hash table from the magazine text. And so we'll end up with two separate hash tables. Each one of them will be of the form like, I don't know, character A, and then that's the key, and then the value will be like 3 or 5 or whatever, depending on the number of occurrences of that letter in the string. And then the rest is just easy. All you have to do is just go through the letter hash table, or either hash table is fine, really. And then you have to make the check of is that character, is the value corresponding to that key less in the letter hash table than it is in the, or equal to than it is in the magazine hash table. And if that condition is not satisfied for any letter, then you return false. And assuming that you get through the entire for loop, you actually get to the point where you just return true because you haven't made an early exit. That was my solution. And you can see here, build hash table for text here is just a private function that I use as a helper. Little, I guess, thing to note here is I deviated a little bit from what's customary in Python in the way that I name my function, but it's very, very common in Swift/Objective-C, where you kind of say build hash table, and then you have for, and then you make it work so that the name of the function itself makes logical sense to anyone who's reading that function. But what I'm referring to is the addition of the for here. So with an Objective-C, you'd have like an actual parameter label, so you'd move that inside the parameter list. But
yeah,
in Python, you restrict it to including that in the function name. I'm not saying
you can do something like that in Python, because like you can have keyword arguments, right? So you can do like def build hash table, and then you can do for equals, and then you can have your.
Oh, that would be then that. Oh yeah, I remember. Did I not use it? I used it
when you're calling it. So you basically have like, this is your thing. This is your kind of variable. So you have like variable, but you have to name it for.
Yeah, unfortunately.
And when you call it, but you can't really, because for is a keyword argument. So you can like underscore for, and then you can like call this function, and then you can do for, and then you can do equals, and then you can pass in your value.
Yeah, I mean, it just works much better in Swift and Objective-C. That's the way I guess you could do it. So maybe like if I were like knowing this, I would still stick to like the for outside of the function name, just because.
Yeah, absolutely. Yeah, this looks bad. Yeah, I take it back.
But yeah, so just descriptive function names, so they work nicely at the call site. Not much else to say about this really. Let's go to method number 2, using Python's built-in collections.counter. So one of the things in EOPI that you're told is that you should know your libraries for hash tables, and one of them is the collection, the parts of the collection library, and that's the counter, which builds a hash table for you based on the occurrences, and it keeps track of the count, basically. And that's nice because you don't have to write the logic for build hash table for it, because it's already done for you. And then when you go from there, this is like straight up out of the book, and you're iterating through the magazine text and looking if that character is inside your hash table that you just created using the collections.counter function. And then if it's there, then you subtract it from the hash table. So you subtract the count from the hash table, and then if the count goes to 0, then that means there are no more occurrences, and you want to delete that key entirely.
Sorry, correct me if I'm wrong, but I think you should index char into your frequency.
Yeah. Oh yeah. Yes. Yeah.
Yeah.
Yeah. Definitely. Absolutely. I don't know. I left that out by mistake, but that's pretty much it. And then you delete it, And if at any point, you and then eventually like you just return not char frequency for letter text. Basically, it just means that if you end up with an empty hash table, then you want to return true because you've subtracted all the letters, and if you don't, then you return false. Let's go to method number 3, which is insane one-liner. Not that insane, but still like interesting, right? Because it leverages collections.counter. Now the question here, like what we're doing here is a set difference, where we're taking the result out of it. We're letting Python do all the work for us, and using set difference is how we get the result. Now, maybe I don't understand this that well, which is why I made a note here. What happens in this case? Like, if you have letter A and 1 occurrence, B 2 occurrences, that's your hash table for your letter text. And then you do the difference with the
the way it works is it just creates the dictionaries with all the letters, and then like subtracting, like it assumes that first dictionary actually is C equal to 0, so it just subtracts C0 from C1, so then it would be C minus 1, but then it doesn't display anything less than 0.
So you wouldn't end up with an empty dictionary then?
You would. The final result would be an empty dictionary. But like in the case that you wanted like a subtraction like this, it just it's not like that letter does not exist in the list. It just subtracts that from 0, is what I mean. Like it implicitly assumes that it's in the dictionary and sets it to 0. But what it actually does is it probably just like says 0 minus that, or just equals to that. You know what I mean?
We can try this right now, real quick. Let me actually do this.
Yeah, because I spent a while playing around with this. I was like, what the hell is going on here?
Yeah.
Because like in a regular dictionary, that's not going to work. It's just in the collections counter.
Oh, it's only in those. So it doesn't overload that.
That's not going to work. It's only when you use collections counter, it like does some stuff behind the scenes that it's smart enough to do that. So like if you import collections and then it's with a lowercase c.
So to follow up on that, so I get it in the case where you've got like a letter that's not there, so it subtracts and it goes to -1, which removes it. But what if you don't have let's say letter A?
Yeah. So look at this example. So it subtracted B, right? But what was B in the first one? There was no B's. So what it did is it just did 0 minus B, and then it doesn't display any elements that are less than 1.
Oh, okay. There you go.
So that's why the thing works. So that's why the whole solution works, is because if the final array has nothing, then that means all the elements in the magazine, like the magazine had enough elements to fill all the other ones, right? Because if you can subtract and get values that are less than 0, that means you had more than enough elements.
Yeah.
Neat.
So that's why it works. It's just you have to know the things that like, it doesn't show elements when they're less than 0 or less than 1, actually. Even if it's 0, it doesn't show it. And the thing that I wanted to point out is the Pythonic one is actually worse than the one above it, because the one above it early ends on the case that you have already filled your like you have enough elements, right? Because you're all constantly going through your magazine or whatever, and you're checking if you can make your letter, and once you can, you're done. You just return true. You're good. But the Pythonic one will just do it for all. Like it'll go through the magazine regardless. So it's not actually as good, even though the book says it is for some reason. Unless it is.
No, the book doesn't say it is. The book says like if the magazine is like super long, then you have to go through the entire magazine.
I think the book says the both are equivalent. No?
I didn't even see the collections counter solution. Wait, this is the solution that I have for 12.2. So it says a brute force approach is to do that, blah, blah, blah. A better approach is to make a single pass over the letters, storing the counter character counts. And then next we make a pass over the magazine. When processing a character, if C appears in hash table, we reduce its count by 1. We remove it from the hash table when count goes to 0. And if the hash table becomes empty, we return true. If we reach the end of the letter and the hash is non-empty, we return false.
They just stuck it at the bottom. If you look at the...
Oh, there's like another one?
No, they just... Look, it was in that picture. The very last line. The very last. There.
Oh, Pythonic
solution that exploits
Yeah, and then there's an orphan line on the next week.
Yeah, I probably didn't.
But it says, note that subtracts only keeps keys. But yeah, like I guess it doesn't say anything about the runtime unless like the Python thing is smart. Like it actually might be that because what we do is we return not that.
Yeah.
So like it might be like dynamically updating. Like it might use iterators, right, to subtract or something.
Yeah.
I don't even know.
It
something
could be
like that.
using iterators under the hood.
There's something smart and
Yeah.
actually be as fast, but who knows?
We still haven't like written a tool that profiles or times these different solutions so that we can
Yeah.
see they're actually better. We just wave hands and talk about it.
Yes.
But yeah. All right. Good.
Okay, that was a long boy, but I hope you enjoyed this, Sina.
It was pretty nice, yeah.
The longest.
Yeah,
definitely
it's
the longest
probably
one.
our longest session so far, and they keep getting longer and longer.
Yeah, we should really try to reduce this.
We really should.
It's an increasing. It's a perfectly increasing time here.
All right, guys. I have
the non-decreasing set.
I have some recommendations for next week. Can we please do problems 15.1 and 16.1?
Yeah, sure. That sounds good.
What are the topics there? What are those chapters?
Recursion and dynamic programming.
Ooh.
And there's like six variants of each of them.
Oh my god, that's
It's actually brutal. Like I didn't do all the variants of. I did like one variant, and then I just like wrote my comments of the other ones because like it was just so long.
Heads up there. I've got a couple of assignments due for that week, and also I've got another ALBUS exam. So that's really heavy. Then I might only like come to the meeting with one of them, like one of the two.
Yeah.
Like a subsection of them.
Okay, if you're gonna do okay, I just have a problem with the one really, and that's, I actually talked to Sina about this earlier.
Yeah.
It's this one here. It's 16.1 variant 1, 2, 3, 4.
Holy shit! That one specifically. So do I have to do? Probably I have to do the normal one. Okay.
You can just give it a read. So yeah, if you guys can come up with that, that's the one I can't figure out at all.
All right, must be pretty damn tough.
I don't know. I was also going to bed last night, so I was like, fuck this. All right.
All right, guys.
Next week.
Yeah, 6th session. Good luck, everyone.
Yeah.
Yeah, we'll see you next week.
Later.
See ya.
See ya.